Welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about higher derivatives. When you find the derivative of a function, it itself is a function, and therefore you can find its rate of change. Because remember, the derivative is the instantaneous rate of change of a function. We talked earlier about instantaneous velocity being the instantaneous rate of change of displacement with respect to time. Now, velocity is also a function and it can change. So if we were to find the instantaneous rate of change of velocity, it would be considered instantaneous acceleration. I'm going to just drop the words instantaneous, and we're going to assume those words are there because I want to explain it so it sounds simpler. We talked earlier how velocity was the rate of change of displacement with respect to time. And now we're going to look at how acceleration is the rate of change of velocity with respect to time. Before we get started on how we find higher derivatives, I want to talk about notation. And there's different ways that we can denote the higher derivatives. There's second derivatives, then the derivative of the second derivative is called the third derivative. The derivative of the third derivative is called the fourth derivative, and so on. So we've talked about some of the different notation we've used for first derivative or for derivatives. Y prime, f prime of x, and dy dx. And another one I'm not putting in here, but the actual function, so d, and then in brackets the actual function, dx. So if we were to take a look at second derivative notation, so y double prime, f double prime of x, and then when we get to this notation, it's a little bit interesting. We go d squared y over dx squared, because it's like this function. It's the derivative of this function with respect to x, but it's the second derivative. Third derivative, triple prime. So for y triple prime, f triple prime of x, and then we get into the third derivative where you'll see that notation. Now obviously we can't keep putting prime symbols down, especially when you're talking about the 10th derivative. So after the third derivative, if it gets any higher, we use a bit different notation. Instead of putting y to the 4 primes, we would use y to the, and in brackets, 4. Because if we just write y to the 4th, that represents something else. That represents a power. So this indicates it's the 4th derivative. Similarly, this uses that same notation with the number of the derivative in brackets. And then this is also used for 4th derivative. We can continue on. So the rule is for nth derivative, so it could be 5th, 6th, 7th, 8th, we're following the same procedures we did with the 4th derivative. So it'll be y, and instead of primes, it's a bracket with the derivative number in there. So if it's the 10th derivative, it would be y bracket 10. If we're finding the 10th derivative, again, we just put that number in there. So this notation is used, and then this notation. So if we had a 10 there and a 10 there, that tells us it's the 10th derivative of our function with respect to x. I don't think you're probably going to have to worry about a lot of these higher derivatives. Typically in calculus, you're just dealing with first and second derivatives, but higher derivatives are used in other areas of math. So, it's good to understand what the notation is, but we're going to be focused more on first and second derivatives. Let's take a look at how we find higher derivatives. So in our first example, if I wanted to find all of the higher derivatives of this function, so if we take a look at the first derivative, we know how to do that. That's going to be 10x to the 4th minus 18x squared plus 7. Now, if you were asked to find the second derivative of this function, all it means is finding the instantaneous rate of change of this function, or in other words, the derivative of this function. So our second derivative would just be the derivative of this. So it would be 40x cubed minus 36x plus 0. Then the third derivative would be the derivative of this. So 120 x squared minus 36. The fourth derivative would be 240x minus 0. The fifth derivative would be 240. And the sixth derivative would be 0. And any subsequent higher derivatives after that would be 0 because we've reached a constant of 0, so the rate of change after that is going to be 0 every time. So the concept of higher derivatives is fairly easy when you're working with polynomial functions. Let's take a look at another example. In this next example, I actually could expand this and it would become a polynomial. So I could do that. If I take x plus 2 times x plus 2, if I square it, I'm going to get x squared plus 4x plus 4. And then I can multiply the x to every term to get x cubed plus 4x squared plus 4x. And then if I want to find the derivative, I differentiate the first function. So in order to find dy dx, I just take the derivative of this polynomial. To find d squared y dx squared, which is the second derivative, I just take the derivative of this, which would be 6x plus 8. The third derivative would be 6. And then the fourth and subsequent derivatives would be 0. But I could also take this derivative using the product rule and the power rule. So my first derivative would be x times the derivative of this, which would be 2 times x plus 2 to the power of 1, times the derivative of what's inside, x plus 2, which is 1, plus x plus 2 squared times the derivative of x, which is 1. We could factor an x plus 2 out, and I'll be left with 2x plus x plus 2 so 2x plus x is 3x. So this is my first derivative. Then my second derivative, again, I could use the product rule. So I take x plus 2 times by the derivative of 3x plus 2, which is 3, plus 3x plus 2 times the derivative of x plus 2, which is 1. And then I could simplify this. And get 6x plus 8. Then my third derivative, now this is the same as the function here, and we can continue. So your rules will still work, your product rule, your quotient rule, your power rules, they still work with second and higher derivatives, but it's usually going to be more work. So anytime you can simplify a function before you differentiate, I highly recommend that you do so. It's not wrong to do it this way. It's correct, but it's just a lot more work. So I always recommend that students take a look at your function before you differentiate it. Is there any way you can simplify it first to make differentiation easier for you? Let's take a look at some more examples. Okay, in my next example, I'm asked to find the third derivative. That's what this notation means. So I take a look at my function. I have 5 over x minus 3 to the 4th power. I could do the quotient rule, however, because my numerator is not a function, it's a constant, I am instead going to write this as a constant times x minus 3 to the negative 4. So I'll bring it out of the denominator, and now it's a constant times a function. If the function had been 5 over x minus 3, I probably would have used the quotient rule on that. Because if I bring it up out of the denominator, I'm introducing a power. It doesn't have a power the way it's written in, as a quotient. So it's going to depend what your denominator looks like when you do have a constant as your numerator. But in this case, I would bring it up because I already have a power, so I just make it a negative power. I have a constant times a function, which is a power, so I take the first derivative, which will be 5 times the derivative of this will be negative 4 times x minus 3 to the negative 4 minus 1 is negative 5. And I could have combined that, just put negative 20. The second derivative will be negative 20 times negative 5, which is positive 100, times x minus 3 to the negative 5 minus 1, which would be negative 6. And then the third derivative will be 100 times negative 6, which is negative 600, times x minus 3 to the negative 6 minus 1 is negative 7, which I could express without negative exponents. But this would probably be a much easier approach than using the quotient rule on that form. Let's take a look at some more. Okay, in this example, we have s, which represents displacement, and as a function of t, where t represents time. And this could be a function for something that's thrown up into the air and has gravity acting on it. So if I was asked to find the instantaneous velocity of this, it would be the instantaneous rate of change of displacement with respect to time. So in other words, the derivative. And I just take the derivative of this function, which would be negative 9.8 t plus 50. So if I wanted to find the velocity at 1 second, I would put a 1 in and I would get positive 40.2. The positive value represents direction, so the object would be going up. If I said evaluate this or find the velocity at t equals 10 seconds, if I put a 10 in there, I would end up with a negative velocity, and what that means is the object is falling down. So the positive, negative, when you're talking about velocity, refers to direction. Now, if I then wanted to find acceleration, the acceleration is the derivative or the instantaneous rate of change of velocity with respect to time. So it's actually going to be the second derivative of displacement. So I take the derivative of velocity, which is this, and it's going to be negative 9.8. And it's a constant because that's the acceleration due to gravity. So any object that gets thrown up in the air or drops down has a constant acceleration of negative 9.8 meters per second squared acting on it. So if you know the units, and let's say our displacement is measured in meters, our time is measured in seconds, when you are asked to evaluate at a specific value, so if I was asked to find ds dt when t is equal to 1, we would put 1 in for t, evaluate, and when we get a number and we know our units, you'll be expected to put the units with your answer. So we're talking about a velocity measured in meters per second. So it's the rate of change of displacement, which is measured in meters, per time, which is measured in seconds. If we were asked to find the acceleration, or the rate of change of velocity with respect to time, at let's say 1 second, our derivative is constant, negative 9.8. Acceleration is constant. It doesn't matter what the time is. So it will always be negative 9.8, and it will be meters per second, which is the unit used to measure velocity, per second, per time. So that would be negative 9.8 meters per second squared. So when you see an acceleration question and you know the unit, you're asked to evaluate it at a specific time, it should include units similar to that. Sometimes you'll be asked to find higher derivatives and you won't be working with explicit functions like we are here. We talked about implicit differentiation in the last video. So in the next video, I'm going to do implicit differentiation, but I'm going to find higher derivatives of those implicit relationships. So once you've had some practice with this, check out the next video.